way. Okay, well, good morning, everyone. Thank you for being here, attending this seminar series. My name is Florence Bouquet. I'm the Managing Director for CREW, the Center for Research and Education in Wind. So today we'll have BrankoKosovic talking. He's got a BS degree in Mechanical Engineering from the University of Rijeka. An MS degree in Aerospace Engineering from Penn State, and a PhD in Engineering, Aerospace Engineering from CU Boulder. Dr. Kosovic worked at Caltech, UC Davis, CU Boulder, Lawrence Livermore, and is now the Program Manager for Renewable Energy at the Research Applications Lab of NCAR. His research focuses on studies of flow, transport, and dispersion in atmospheric boundary layers using LES. He specializes in subgrid modeling of turbulence in stable stratified flows, and he's currently working on expanding multiscale modeling capabilities in the WRF model for wind energy applications. And so today, Dr. Kosovic will talk about multiscale simulations of flows in atmospheric boundary layers.
Thank you, Florence, and I would like to first thank CREW and Florence and Kurt for inviting me here to talk to you about my research. Florence already mentioned the title of the talk, so I just want to acknowledge my colleagues and collaborators that worked on some of the work that I'm going to present today, and that's Jeff Miroka from Livermore, Katie Lundquist also from Livermore, and Julie Lundquist from CU. So I start with this puzzle, multiscale modeling challenge. It's a puzzle that some 50 years ago, inspired by ideas of Richardson and von Neumann, Manabe and Phillips and others started solving by developing global circulation models. About 10 years later, first mesoscale models, limited area models were developed. One of them is, for example, the ancestor of mesoscale MM5 model that you heard of, which is also the ancestor of WRF model. And that was MesoMonster, developed by Rick Antis and Tom Warner, late Tom Warner, who was my boss when I came to NCAR. About the same time at NCAR, Doug Lilly and Jim Deardorff were developing larger dissimulation for simulations of flows in atmospheric boundary layers. Early on, those simulations were focused on canonical, flat plate, homogeneous boundary layers. And that went on for a number of years. And only recently, in recent years, we see developments of larger dissimulations of flows of more heterogeneous terrain. Another challenge that's presented when simulating atmospheric boundary layer flows is stable boundary layers, in particular strongly stable boundary layers. That's still a challenge and a very active area of research. Development of high-performance computing and numerical methods and codes for numerical weather prediction has evolved over time. And now, with new models like WRF, COMS, or ARPS, we can bridge the scales between mesoscale and LES. However, additional work needs to be done to achieve that. And there are a number of applications for which we would need that. For example, dispersion in urban environment that are very complex, or simulation of flows of wind farms that are essentially developing boundary layers, internal boundary layers, that are developing in the heterogeneous. So the question is, why are scale interactions important? I start with an example that's close to us here in Boulder. Unfortunately, this summer there were a number of fires in Colorado, and there was one in Boulder that threatened Boulder. It was just a mile from our house, and we watched it carefully. As you see, the fire was in very complex terrain. That was the source of the fire, and there we see on the screen fire retardant being dropped on the source of the fire. As the fire developed, as the day progressed and convective boundary layer developed, the plume from the fire was lofted, and then large scale flows advected it large distances. Then in the evening, as the stable boundary layer developed and drainage currents flowing down from the mountains, the smoke from the fire came down to downtown Boulder. So on this example, we see how a wide range of scales are spanned, and how mesoscale interacts with boundary layer flow, and also the effects of complex terrain. Another reason why we are now looking at multiscale simulations is that we can. In the past, we were not able to do that. But new developments in computational capabilities are enabling that. John Mikalakis is here, and I watched his presentation in the WRF Users Workshop, where he talked about testing WRF on Intel's many integrated core platform, new platform that has 50 cores, and can achieve close to 1 teraflop per second peak performance. Similarly, development in graphics processing units like NVIDIA Fermi allowed that kind of performance. And there was a talk recently at the 20th Symposium on Boundary Layers and Turbulence by Jerome Schkalkwijk, who presented the simulation, large simulation of entire Netherlands with 4,000 grid points by 4,000 grid points in horizontal. So, because it's possible, now we are moving in that direction. Oops. Huh. Interesting. Something didn't get translated on this slide. I don't know why. That's for the audience here, I'll try to quickly switch to my presentation, because I'd like to say a few words about this slide. And I apologize to the audience, online audience. It's just a plot of, yes, I know. So it's a plot that shows on a vertical coordinate grid cell size in kilometers, and on the horizontal the time from 1970 to present time. And it shows how resolution of different types of simulations increased over time, or how grid cell size diminished. So in red diamonds and blue squares, we show numerical weather prediction codes and their resolution. When they first developed, the resolution was on the order of 100 kilometers or so. For operational research was within tens of kilometers. DNS, we know we have to resolve turbulence completely, so it's always at Kolmogorov scale. And LES started with about 100-meter grid cell size resolution when Deerdorf did his first simulations, and now it's down to 10 or less meters. We see that resolution of numerical weather prediction simulations is approaching LES, and actually in research mode, some people are running numerical weather prediction codes at a few hundred meters. Now the question is whether that is okay, and that's still to be addressed in the future. But it's obvious from this slide that these two types of simulations are getting closer and closer and merging, and we have to answer the question, how are we going to do that properly? So I'm going to go back to In the past, as I said, larger simulations were focused on canonical flat plate boundary layers over homogeneous terrain. And this is the usual picture of the spectrum of turbulence that we can obtain from such simulation, where we resolve the peak energy containing scale in boundary layer that's of the order 1 kilometer. And we don't care about what's happening at a larger scale. However, boundary layer is embedded in the atmosphere, and there are scales of energy on larger scales. So this was traditional view and traditional view because we were limited with what we could do. So, and also this traditional view was motivated by spectrum, an old spectrum for Van der Hoeven from 1957, where this separation of scales between boundary layer scales and mesoscales was observed. And this separation of scales we see here in this spectral gap between boundary layer scales on the right and mesoscales on the left. This spectrum was observed at Brookhaven with that's coastal location with a fetch from the ocean. So and potentially also stable boundary conditions for the most part, where warm air was flowing over cold ocean. That kind of spectrum is not in general observed. And here we have a spectrum from, in blue color, from Cabau Tower in Netherlands, where we see that such a gap doesn't exist. We see some peaks for diurnal harmonics, but then the spectrum falls off at something that's about -5/3. So that kind of gap most often is not observed. And Cabau location is also very flat. It's more inland, but it's very flat. So the question now arises: what kind of flows and structures interact, create that interaction between mesoscale and boundary layer scale? And here is just one example of cloud streaks that indicate existence of convective rolls. And these cloud streaks are often observed in satellite images. And here I have just two examples: one at Bering Sea, from Bering Sea, and the other one from Oklahoma. On the right, I put a scale of distance between Oklahoma City and Wichita in Kansas, which is about 250 kilometers. And when you compare that with the scale of these streaks, you see that they are really of that scale. So these are not, although they are in the boundary layer, they are not boundary layer structures, they're mesoscale structures. And actually, when we do larger simulation at very large scale, that's 12 kilometers square in this case, at stability parameter Zi over L. Zi is a mixed layer height, boundary layer height. L is monobukov length scale of order -10. We observe this convective rolls. This is vertical velocity, positive. This is negative. So we observe those rolls, and their stream-wise dimension is 6 kilometers or larger. Maybe this one is even larger, and so they cannot be considered boundary layer structures or microscale structures. They cross-stream, in cross-stream direction, they scale with boundary layer height, so that can be considered as microscale. Wow. So again, something happened in conversion to PDF. Equations are missing. For the audience here, I'm going to again switch to my presentation. So for the purpose of simulating flows over, from mesoscale to microscale, we'll use weather research and forecasting model, or WRF. That's community-based, community-developed model that you probably heard about, so I'm not going to go into great detail. I just want to mention that WRF includes larger dissimulation capability. It includes two subgrid moles. One is Smagorinsky, the standard Smagorinsky mole, and the other one is nonlinear mole. Nonlinear mole is the mole that I actually developed here at CU for my thesis, and it was introduced in 2010 by Jeff Miroka et al. Into WRF. So now it's available in WRF. It's available and tested and validated. The nonlinear mole extends the idea of Smagorinsky mole that represents the drain of energy from resolved scales to subgrid, but because we know that in addition to drain of energy or dissipation or transfer of energy from large scales to small, there is also interaction that creates a backscatter of energy from small scales to large scales. I introduced an additional term, and this middle term represents that backscatter of energy. The third term is there because in sheared homogeneous flows, Smagorinsky mole cannot represent normal stress effects at all. And they exist, they can be measured in sheared homogeneous flows. So that second term was added to represent those effects. Parameters, we now have two additional parameters, but it can be shown that they should be equal, and they can be related to backscatter parameter. Backscatter parameter can be then determined either theoretically, that's some theoretical estimates, or it can be determined from DNS if you have DNS at the appropriate Reynolds number. So again, I'm going to go back to the online presentation, and I'm sorry you were not able to see the equations. So before we embark on the modeling flows across the scales from mesoscale to LES or microscale, we need to extensively validate the WRF for simulations of flows over various terrains, including heterogeneous terrains. And as the first step that I took is to validate WRF LES for flow over Askeran Hill. Askeran Hill is an experiment that took place at the beginning of the 80s, and Taylor and Tennyson reported in Boundary Layer Metrology on that experiment, the number of papers, and it's a case that's often used for validation of either CFD codes or mesoscale and LES codes for flows over complex terrain. Askeran Hill, yes?
Why do people still use the Askeran Hill experiment?
So the question is, why do people still use Askeran Hill experiment? Because there are no better experiments. And I know that right now one experiment is planned in the United States. It's called Matterhorn experiment, but it will be a couple years before the data from that experiment are available. And that experiment is, the Matterhorn mountain is, actually it's not Matterhorn mountain, the experiment is Matterhorn. The mountain is much taller than Askeran Hill, so that will be much more complex. But in terms of number of instruments, it's going to surpass what was available then. Simply, there are no good comprehensive experiments. And that's why this one is used. And Hill is relatively simple, so it lends itself as a first step in validation of numerical simulations. The hill is on the southwest island in Scotland. It's on the west side, facing Atlantic Ocean. And it was instrumented by 50 10-meter towers and 2 tall towers. One tall tower was to characterize inflow, and the other one was on the top of the hill. Here is the counterplot of the hill. Hill was about 100 20 meters tall. And this is the domain that I use for simulation, so I rotated the hill. The north is now in the upper left corner. And the white arrow indicates the direction of the wind. Here we have also 3 lines. These are the lines along which 10-meter towers were positioned. And these are lines A, AA, and B. Also that points HT, that's the top of the hill, and CT, the another point on the ridge of the hill. RS denotes the reference position of the reference tower. So I use the WRF's nesting capability to do the simulation of flow of heterogeneous terrain. Nesting in WRF, in particular one-way nesting, allows us to, on out-to-nest, to use periodic boundary conditions as indicated on this slide, and use it to spin up turbulence, realistic turbulence, with realistic forcing, large-scale forcing. And then we can embed one-way nest, finer nest inside that represents terrain, and it's one-way nested. So what comes out of the inner nest here doesn't get back to the outer nest, and therefore will not come back in as inflow to this inner nest. So now we can carry out simulations of heterogeneous terrain with realistic inflow conditions. And here we have an animation of the flow of the vertical velocity over Askewan Hill from this larger simulation. We see positive vertical velocity on the upslope and negative on the downslope. And unfortunately, again, animation doesn't work through Adobe. So for audience here, I'll just start the animation. So one thing to notice in this animation is how much velocity, vertical velocity fluctuates at the top of the hill. And that's the location where we put our turbines. So this significant fluctuation of vertical velocity needs to be captured and represented well, so that we know and can compute the loads on the turbines if we decide to put them at that location. The next animation, and I'm going to show it here for the audience in the room, is the animation of turbulent kinetic energy in this case. And we see significant turbulent kinetic energy in the lee of the hill. It develops as the shear develops, as we have flow over the hill. Eventually, this turbulence will act in reducing the shear, and it will be advected and dissipated. The shear will be reduced, so there will be less turbulence produced for a while, but then the flow will accelerate again. We'll have again high production of turbulence and development of this turbulent peak at the lee of the hill, and this process repeats itself. So it's very intermittent.
What determines that period?
The period is determined most likely by the width of the hill, and the height of the hill, and the wave that forms in the lee of the hill. I didn't do the exact analysis. But yes.
So do you have the intense?
No, because what goes out doesn't come back in. This section is not periodic. Only outer domain is periodic. Inner domain is not periodic, and it's one-way nested. So what comes out of the inner domain does not go back into the outer domain.
Does the wind speed slow down with time, or do you have some kind of force or what?
there is geostrophic forcing. That's a large-scale pressure gradient that forces us. So these were more qualitative examples, and now we'll do more quantitative comparison of our large eddy simulation results with measurements. And in this slide, I show the speed up along line A, and that was presented in a previous slide. Diamonds represent measurements at 10-meter towers, and lines represent results from WRF LES with 4 different subgrid models, actually 2 subgrid models in 2 variants. I said we have Smagorinsky model and nonlinear model. Each of them can be used with prognostic equation for turbulent kinetic energy, and that's what's shown here. And we can see the nonlinear model with prognostic equation for turbulent kinetic energy performs best in this case, and quite closely follows the measurements until the lee side of the hill where it over-predicts the speed up. And that's a common problem with numerical simulations. This is a similar plot for line AA. So line A went through the top of the hill, line AA went through another top on the ridge of the hill. Again, nonlinear model has the best performance with the underperformance of all the models in the lee of the hill. And this is the comparison measurements across the ridge of the hill with LES. And in this case, again, nonlinear model shows the best performance, while other models over-predict the wind speed, the speed up across the ridge. NBA TK includes prognostic equation for TKE. So, and based on that TKE, for subgrid TKE, we estimate the eddy diffusivity. Otherwise, we use classic Smagorinsky eddy diffusivity, which is related to strain rate magnitude. Yes?
Is there a difference in computational time between NBA?
It's slight difference, just carrying out additional prognostic equation, which is really, I don't know, 10% or less. Finally, we compare the turbulent kinetic the turbulence intensity that was measured. Unfortunately, stresses or fluxes were not measured, but turbulent intensity was. And here we have, again, in diamonds, turbulent intensity, and lines that represent our simulations. And we can see that Smagorinsky model in both forms underpredicts turbulent intensity, which is not totally surprising because it's overly dissipative, while nonlinear model overpredicts turbulent intensity in the upwind from the hill, but then captures the intensity at the top of the hill. And here we have, in both cases, we show models with prognostic equation for TK because only those can give us the total TK. So if you don't have a prognostic equation for subgrid TK, we don't do comparison. And here I split the total TK and the subgrid component. Total is in solid line, blue line, and dashed line here, and dash dot is subgrid TK for nonlinear model, dotted line is subgrid TK for Smagorinsky model. So this was validation of WRF for the flow of Aspen Hill. For applications in wind energy, we want to do simulations of a flow of a wind farm. In the past, those simulations didn't include all the atmospheric effects. because they were done with CFD codes that were engineering codes that don't include all the atmospheric physics and atmospheric processes. Also, they depended on boundary conditions from numerical weather prediction models that are often very different they apply different numerical schemes. It's not easy to implement the coupling between NWP models and CFD models. And sometimes they include unrealistic periodic boundary conditions, which result in essentially infinite wind farms. Those are still valid studies. They inform us about properties of these flows, but those are their limitations. We would like to move beyond those limitations, and carrying out multiscale simulations from mesoscale to LES would be the goal. To achieve this goal, we implemented an actuator-disk model, generalized actuator-disk model in WRF to represent the effect of the turbine on the flow. And actuator-disk model uses blade element theory. Generalized actuator-disk model just distributes that over the grid in a simulation. And smears the effect of the turbine over the rotor disk. Another step would be to represent each individual blade using similar model, and that would be actuator line model. However, we didn't do that because our target resolution is really few meters, 5 meters, and to represent the effect of each blade separately, we would need to go below 2 meters. And that's, at this point, not our goal. So this is an example of what output from such an actuator-disk model looks like, and this is a high resolution that what we use in larger disk simulation. This is a 1 meter resolution. But just as a demonstration, we implemented a realistic shear and turbulence, and then computed both the normal, the thrust and the rotational effect of the turbine rotor. And here we see just tangential forces that have maximum at the top of the rotor and minimum at the bottom. And that's because we implemented the shear across the rotor plane. If you look at the thrust profile over the rotor, this is the picture we get. And again, because of that shear, we have a maximum at the top of the rotor. And we see here the effect also of random fluctuations. This is just demonstration what the effect of the actuator-disk model is. And now we we try to simulate an array of 4x4 turbines that were placed similarly, like in, yes, there's a question here.
How close is the parallel turbines to the edge?
So this is not to scale. It was at least 1 kilometer because we had 400 points, 440 points at 10 meter resolution, and rows of turbines that spaced about, I think, 700 meters or 800 meters, something like that. So yeah, at front we have about 1 kilometer. And that's important to allow for the flow to develop on the inner grid, because it's coarser on the coarser grid, and turbulence needs to cascade down to smaller scales. So again, a simulation that unfortunately doesn't play on the Adobe. So for the audience in the room, I'll show the animation of the flow through a turbine array. This is a top view. Top view through the rotor plane, through the hub, actually, of the turbines. And we can see as the bakes and turbines develop, and they meander and there is entrainment of high momentum fluid behind the turbines from the space between the turbine rows. And the wakes get stronger as we go down through the turbine array.
What was the resolution?
We have the rotor disk was 80 meters, and the resolution was 10 meters. So we have 8 grid cells across the rotor disk.
I have a question.
Yes?
So just to make sure I have this straight, you solved the inner nesting grid?
That's yes. They are not fully coupled. That's the thing. It's one-way nesting. So the inner nest is coupled to the outer nest. The inner nest gets information from the outer nest, but inner nest does not pass information back to the outer nest.
And so that's why the wake
Right.
distance doesn't affect the inflow.
Exactly. That's why wake from the turbines that's developed on the inner nest doesn't affect the inflow that comes from the outer nest.
How the turbines are how you do that in the equations?
Yes, that's essentially through the. I don't have the details here of the actuator disk, but actuator disk model represents the effects of thrust and torque of the turbine through just forces, body forces, that are distributed over the rotor disk. And that body forces are computed from blade element theory that's used for design of blades. So we have to know the characteristics of the blade, the profile, the pressure, the drag coefficient for the blade. And from those, we can compute lift and drag. And then from lift and drag, we can compute thrust and torque. Yes.
What's the mean torque the actuator disk model with track with the LES?
We'll see that just in a moment. So the question was, how does the torque of the turbine interact with the flow? And here's the, again, animation that I'll have to switch back to animations, but for those online, you can see the three-dimensional visualization of wind turbine array and entropy in the field. And entropy is vorticity magnitude. So these turbines essentially generate vorticity in the flow field. And as we go from the front row down through the array, more and more, we see more and more entropy, more and more vorticity, small-scale vorticity generated.
Do you use a power cable?
Yes. Do I need to use it? Okay. Just a moment. So, again, for the audience in the room, so this is how the turbines affect the flow by generating vorticity through this, through torque. And in this case, it's because the effect of the turbine is distributed over the rotor is not exactly the same as in reality, where the vortice is developed over the blade and then shedded from the blade. But the level of vorticity introduced should be similar. Yes?
So we see these blobs of yellow, and that's just because of the threshold level that contouring, and and the inflow is inhomogeneous.
Right.
So sometimes.
So right, the inflow already has some vorticity in it because it's a boundary-like flow that has its own vorticity. But that vorticity, especially smaller scales, are enhanced and developed further, produced further through the array.
So the entropy is created.
Right.
Vorticity that comes, the idea is it's small scale vorticity that shut off
The
the actual
blades, right.
Some vorticity.
Well, it's represented that way, like a spinning of the entire system, but in reality, it comes off the blades. But the forces that create that are the same, except in the actuated disc, they are smeared over the whole rotor. And in actuated line, they would be coming off the lines or blades. Yes, there is a source of vorticity associated with blades that in this case, it's smeared over the whole rotor disc. If you had the actuated line, they would be coming off the blades. So it is actually blades that generate that vorticity. But in our case, we smear that effect over the whole rotor disc.
So if you could divide somehow just sort of
Yes, I would imagine yes, but yes, another question.
So the discs, are they rotating or are they?
Well, they're not physical disks. They're just body forces. So they're just body forces.
Is there a rotation?
But the rotation is accounted for. Yes, yes, that's how you get the tangential force because of rotation.
So other groups have talked about an actuator disc that's rotating and an actuator disc that's not rotating. And is
This would be the one that's rotating, and although there is nothing that's rotating, it's just that the effect of rotation is imposed on the flow. And finally, again, another animation that just oops, sorry. Shows a side view of the same turbine array. And here I want to demonstrate the effect of entrainment of high momentum air from above the turbine. From top view, we saw entrainment of high momentum air from the sides. Here we have entrainment of high momentum from the top. And we can see that in some cases it gets entrained quite soon after the turbine. And some of it is from the top. In this case, it's hard to say. Some of it also can be from the side. But we can see that definitely this is coming from the top. So that's how the bakes can recover, and that's why it's important to space turbine rows accordingly to extract the most momentum from the flow, and not affect the downstream rows of turbines. So we still have a lot of work to do on this, actually, the disk model, as we can see from this plot, where we have a comparison of essentially the power extracted at or wind speed at different turbine rows. So this first row represents inflow, and we match the inflow in LES to the inflow that's observed in a wind farm. I have to say that these diamonds, the observations that the diamonds are obtained converting the power extracted from the turbine. So not actually measuring wind speed, but converting power to wind speed. And we didn't compute power in our simulations, but we just computed wind speed. So on both sides, there can be errors when comparing this. But as we can see, our simulations overpredict the wind speed, the relative wind speed at the downstream rows of turbines compared to what was measured from power in this case. And this can be attributed to the fact that we really didn't have the actual information about the turbines that were installed in this wind farm, but we created our own that may not be as efficient in extracting the momentum. The dimensions were the same, but the characteristics of the blades were not. Also, our resolution may still be too coarse at 10 meters, and we are now carrying out finer grid simulations. So, as I said, there is still work to be done.
Was the stability of the atmosphere?
No, it wasn't. There could be other effects. That's true. There could be. We did numerical simulations with neutral flow. This is an offshore wind farm. It could have been an effect of stability, definitely. So at the end, there's a lot of work that still needs to be done to achieve this goal of multi-scale simulations across scales from mesoscale to microscale. And I just at the end listed a number of questions, and maybe to motivate some of the students here to work on some of these problems. But the questions are, how do we address non-existence, actual non-existence of a spectral gap between mesoscale and microscale? How do we then do transition from PBL schemes used in mesoscale models that are based on ensemble averaging to turbulent schemes in larger simulations that are based on different approach? When we are faced with heterogeneous boundary layers, we don't know really what to do with a lower boundary condition. For nice homogeneous boundary conditions, boundary flows, we can very safely apply a book of similarity theory that gives us lower boundary condition. However, when we have heterogeneous developing boundary layer over terrain or over heated surfaces or through a wind turbine array, the assumptions that went into developing a monobook of similarity theory are broken. So we are still using it because that's the only thing we have, but really we have to think whether that's the right thing to do. PBL parametrizations in mesoscale models, as they are developed today, they all assume horizontal homogeneity. And when we are going from tens of kilometers or kilometers down to hundreds of meters, that assumption breaks down, and we have to modify those parametrizations. PBL parametrizations are based on ensemble averaging ideas. LES are based on filtering. So what is the approach that we take when we try to do multiscale simulations? We need also better ways to observe heterogeneous boundary layers. And finally, last but not least, we have to define what's required accuracy and what's acceptable uncertainty. As we are facing heterogeneous boundary layers, they're all going to be different. They're all going to depend on different forcings. And having, we are not going to be able to do idealized experiments. However, we have to extract as much information from these experiments, enough information that's sufficient for the applications we have at hand. We are never going to have ideal results. So with these questions, I end my presentation, and I'm open for questions.
So I have two questions about the spectrum. how general would you be prepared to make that statement? Because at the very least, at mesoscale, so you would have a 2D inverse cascade and a microscale, so whether or not there's an actual gap, it would at least be different regimes. It may be the case that you have smaller, for instance, that may increase the that's my first question, is basically how general is that statement? Also, does it matter if there's a second? Because if you have enough resolution, we'll resolve that large scale business.
So the question was first whether the statement about existence or non-existence spectral gap can be generalized, and considering that mesoscale spectrum has very different characteristics than microscale, that spectrum is still in most cases measured as minus 5/3. However, most people don't think that it's just inverse cascade like in two-dimensional turbines. It's probably something that it's still just forward transfer energy. I think it's probably some combination of the two.
And it's hard to tell the difference between K and -5.
That's true, although if you look at the papers, most of them claim it's minus 5/3 now. And I'm not expert on mesoscale, so that's just what. So yes, sometimes that gap exists. Why is it important? It's important because that allows us to separate the scales and say, I'll model just mesoscale, and in a very simple way, a simple statistical way, represent the effect of boundary-layer scales. Now, and if the gap is full gap where energy would go to 0, that means that there will be dissipation at mesoscale, which is not there. So there's always some energy at those scales. The fact that there is always some energy at those scales means that there will always be some scale interactions through those scales that will have to be represented. And that kind of then ties to the second question. And the answer to the second question is yes, if we are doing LES over the whole domain, we would not worry because the energy would cascade naturally, as it would in reality, and would be dissipated where it is now at Kolmogorov scale, or we would put filter cutoff in initial range and represent the transfer energy further on. However, we are never gonna, well, not never, I'm not gonna say never, because we saw a simulation of LES over the entire Netherlands. So, you know, students sitting here in 50 years may see simulations of LES simulations over the whole globe. But in a foreseeable future, we are not going to see that. So we'll always have to embed LES within mesoscale. And then all these questions arise. How do we do the transfer from one to the other? Because in both, we'll have to represent the transfer energy. And how do we do it is the question. I hope that kind of answers your question. Yes?
That's a question about water. It doesn't use height as a vertical coordinate.
Right, that's true.
Yeah. Does this present any kind of problem when you've got structures fixed?
Yes, you have to recompute the location on the grid. And there is work done at Livermore where Katie Lundquist, one of my collaborators, introduced, and Julie Lundquist here, they introduced an immersed boundary condition in WAR to simulate flow in urban environment where buildings are represented. And in each time step, they have to recompute where the buildings are. And that's computationally expensive right now. I mean, it can be improved, and that's, again, area of work. Any questions?